continue. So we finished with the model that is described by some equations with the combination of linear terms, quadruple terms, and so on. Now the next idea. The next idea is Kolmogorov model. The main idea is to consider any functions that satisfy some conditions. And we'll see that this situation is more general, but still have them still contain same features as previous models. So, the Kolmogorov predator pre-model, equation 24. As usual, the first are our victims, and the second are predators. But now the functions who are responsible for dynamic of one population, K1 and K2, and the function that reflects the interspecific interaction. Now they are functions. First of all, we need to understand what are the features of these functions. The first moment, all of these functions depend on N1. All of them depend on N1. So it means that interspecific interaction of predators, interspecific interaction, and intraspecific interaction of victims, all of them depends only on the victim's number. What does functions K1, K2, and L mean? Yes, as usual, we consider only continuously differential functions when N1 belongs to interval from 0 to positive infinity. We do not consider negative N1 because of biological principles. So let us consider only the first equation with the absence of predators. So this one. So no predators. And our equation must be our usual equation with self-limiting and so on. Let's try to plot a draw of the function K1. N1 and K1. The first question. So K1 from 0 to positive infinity. And what is the sign of K1 of 0? How do you think? Should K1 be positive or negative? Or maybe K1 of 0 is 0. Well, it seems I will not get the feedback. Well,
sorry, can you repeat your question?
K1 of 0. What is the sign of K1?
Sorry, I have a problem with my not microphone, наушники. That's why I should take a second.
Something like earphone.
Thank you.
Well, ear something. Well, okay. Can anyone answer? What is K1 of 0? How do you think? Is it positive or negative? Well, the equation in the absence of predators, it is our usual one species equation. So if the number of victims is small, is it close to 0, then we expect that our victims will replenish, the number will grow. So at the beginning, at the origin, when K1 is 0, the K1 must be positive. So K1 of 0 must be positive. So the solution will grow exponentially in the absence of our predators. What's next? When the amount of victims is going to increase, then self-limiting arise. And so far, at some the reproduction coefficient K1 will start decreasing with time. And at some moment, we'll see that there exists the capacity of the environment. Let it be A. So far, K1 of A must be equal to 0. So our victim population will stabilize near some quantity A. And then with further increase of N1, K1 will decrease more and more. So from the mathematical point of view, we can describe it into two statements. First of all, K1 is decreasing, and the second, K1 change the sign from 0 to infinity, from positive to negative. So these are main features of K1. What about K2? What about K2? Let's try drawing the same picture for K2. When the number of victims is small, then our predators are dying. The less there is, the less there exists food, the quicker they die. So K2 of 0 must be negative. This is some K2 of 0. Then, with further increase of the victims' number, our predators will change from dying to increasing the quantity. So the picture will be like this, with some point B. What does B means? It is the minimum quantity of victims that support the population of predators. And we'll see that in this model, the most crucial thing is what is bigger, B or A. We'll see it a bit later. And the function L of n is called a trophic function of the predator. It equals to the number of victims consumed per unit of time by one predator. Since we multiply the predator number by the function L, so it is the speed of consuming of victims. And it's quite natural that L of 0 is 0. It means that if there is no victims, the consuming is 0. And if there exists some victim population, then this consuming speed will be positive. We have no ideas of the shape of this function. We just consider it any continuously differentiable function. What can be the shape of this function L of n? It depends on the hunting abilities of our predator. So n1, and let us consider L. There are some different situations in the real world. Some of predators are able to hunt for a long time, and if, for example, a wolf see a rabbit, if he smells a rabbit, he can go step by step for 2 or 3 days. And finally, a wolf will kill this rabbit. So if there is a small population of rabbits, then if there is no rabbits, so our wolf is hungry, he kills none. But if there is a small population, then a wolf quickly, this L function will quickly grow up and then stabilize near some value. So if there is enough of the food, our wolf kills as they need. There is some maximum consumption, maximum amount of biomass that can be consumed by one wolf. So it is this maximum value. Another situation, when our predator is, for example, a whale, and he is fed by plankton, so the amount of food depends only on the density of the food in the ocean. As the whale just is filtering the water, if the population of our plankton is large, then he still stop feeding, but the function looks more linear. So this is our wolf. Here is our whale. And there can be another bad situation when the predator has some troubles in hunting, and their predator can survive only if there is a lot of food. So if the density is small, he cannot hunt, and he can die of starvation. So there can be 3 different types of our function L. But usually the shape is close to one of them. Next, let's try to find our steady states and analyze their stability. We'll use our features of function k1 and k2, and it will help us to understand the nature of our steady states. So, first of all, in the equation, there can exist no more than 3 equilibriums. The first one, let us try to solve we are solving the equation k1 of n1 n minus L, no space. I'm gonna rewrite it. The equation k1 of n1 minus L of n1 n2 and k2 of n1 n2 is 0. So solving the second equation give us n2 is 0, and since we know the shape of the function k2, we get 2 equilibriums. The first, when k2 I'm sorry, when n2 is 0, the right-hand side of the first equation is 0, and we have 2 options. The first option is n1 is 0, it is our point m0, and the second, from the equation k1 of n1 is 0, and we denote k1 of a is 0, so the point m1 will be a0. And another point, another solution of our algebraic equation is when k2 of b, this one, is 0, we replace with our n1 with b, and we get these equations for b and c. Sometimes there is a question, will c be positive or negative? From these equations, c is k1 of b divided by L of b. B and L of b are both positive, and k1 of b can be positive or negative. That depends on the position of A and of B. So we remember that K1 of A is 0. So if B is greater than A, then C is positive. So our Kolmogorov model have a positive solution. So our species can coexist. And otherwise, if B is smaller than A, then C is negative. So at this case, only M0 and M1 exist in our model. What is the biological meaning of B? The biological meaning of A is the capacity of the environment for our victims. And what is the meaning of the point B? It is the number of victims that can feed predators. So far, if B is greater than A, it means that the number of victims that is needed to surviving of the predator population, this number is greater than capacity for the victims. It means that even if there is no predators, our victims, our optimal point for victims is smaller. It means that in this model, there is not enough food for our predators and they will die. And we'll see it from mathematical point of view. And if our B is less than A, that means that the number of victims needed for survival of our predator population is smaller than capacity for our victims, and it's okay. We expect that both of our species can coexist. So we can use the same linear approximation method. We calculate the Jacobian matrix of our right-hand side of the equation. So we just calculate the f by the n, and then we apply coordinates of our equilibriums to this matrix. So if we consider the point M0, 0, 0, okay, so let us consider 0, 0. N2 is 0, L of 0 is 0, N2 is 0, N1 is 0. So far, our matrix will become K1 of 0, K2 of 0. A diagonal matrix with these diagonal elements. So far, the eigenvalues are K1 of 0 and K2 of 0. They are real. Both of them are real and have opposite signs. The first one is positive and the second one is negative. So far, we conclude that our equilibrium point M0 is unstable. Next one. Consider the point A0. The linear approximation matrix is K1 prime of A, negative L of A, K, Now 0, K2 of A. In this form, so the system is the system of our linear approximation, and the matrix is written to the right. So the matrix is triangular. So eigenvalues are on diagonals. K1 prime is always negative, and K2 of A K2 of A can be positive or negative. If B is smaller than A, then K2 of A will be positive. And since eigenvalues have opposite signs, the equilibrium is saddle and it is unstable. Otherwise, if B is greater than A, then K2 is negative. Both of our eigenvalues are negative. And finally, we conclude that singular point is a stable node or degenerated node if our eigenvalues are the same. But still, it is stable. And finally, if their condition A greater than B is fulfilled, then the point M2 exists in our N plus, and the linear approximation give us a bit more complicated equation. And when we consider the eigenvalue problem, we can conclude that, so we denote sigma as this quantity, negative K1 prime of B, B minus K1 of B plus L prime of B multiplied by C. So if this sigma is positive, then the point M2 is stable. And if it is negative, then the point M2 is unstable. But still, there can exist some stable limit cycles around. It's not that complicated. We just find the equation for eigenvalues, and we can easily see that it is the condition for our eigenvalue problem. So if sigma is positive, then all the roots of our eigenvalue equation have negative real parts. So far, there is 3 types of our dynamics in Kolmogorov model. If A is smaller than B, the last situation, there exist only 2 steady states. M1 is stable, and it means that there is no coexistence. In this situation, the predators will extinct, and then our victims will stabilize near some point. And all three other variants, sigma is positive, so there is our point M2, M1, and M. 0. So we see a node. It is stable, so all of our trajectories are going to M2 with time. And another situation, when sigma is negative, then our non-trivial solution is not stable, but there can exist limit cycles, or there can exist some more complicated dynamics in this case. And in all these three situations, the point M1 is unstable. It means that sometimes both species can extinct, but usually I'm not sure this picture is valid. I'm not sure. I think they should go something like this, because zero solution is a saddle. So the shape of the curves look like this. So they can be more complicated dynamics, but they will not extinct both of them. Both of them do not extinct. So far, we see that our Kolmogorov model is the generalization of Lotka-Volterra equation. It has all the dynamic types that we have seen in Volterra equation, but moreover, we have another interesting situation with the limit cycle. Another two simple models. We did not consider to another type of interaction. There can exist competition between two species, and there can exist something like symbiosis between two species. So let us consider competition first. As usual, we have two equations. Let Ci be reproduction coefficients, and Aij intraspecific coefficients, and interspecific competition coefficient. So far, we can see that both are victims. Both of them are victims. So they do not eat each other, but they compete for some resources. So they share resources, and therefore two populations compete. Let us consider first the situation when all the coefficients C, A, and B are the same for both populations. So far, the population are absolutely identical. let's consider that they are different, but all their interaction is identical. It's an interesting question. What will happen in this model? So who of these species will survive and who will not survive? The same analysis as in previous case. We find out the equilibriums. So we solve this one equation. And we see that our system have 4 different positive solutions. Positive or non-negative. 4 non-negative solutions. There are 4 steady states. 0, 0, it's okay. So there is no species. C divided by A, 0, 0, C divided by A. These 2 points means that the first means that the second species extinct and the first stabilized near some point, near the capacity of the environment, and point P2 when the first species dies. It's interesting where is this watershed, what is the border when one species dies and another survives, and the same when the first survive and the second dies. We'll see it on the picture. And there is another one, the point P3, meaning that there can be their coexistence. So when we find the matrix of linear approximation and we find the eigenvalues, we can conclude that the dynamics depend on the difference between A and B. Let's refresh our memories. What is A and what is B? Since in the equation in the right hand side we have n1 dot is negative A n1 square. It means that A reflects interspecific interaction and B reflects intraspecific interaction. And what is stronger? If the species compete with each other more strong than they compete with another type of the species, then A will be greater than B. If the interspecific competition is more strong than intraspecific, then B will be greater than A. So finally, the stability of all 4 points is determined by this table. Zero solution is always unstable, and points P1, P2, and P3 depends on the sign of A minus B. So in the first situation, the points P1 and P2 are unstable, and the non-trivial solution is stable non-trivial equilibrium is stable so far if the species compete each other stronger than they compete with enemy population, then they can coexist. And if the intraspecific competition is more strong than interspecific, we see that they do not coexist. They do not coexist, but there can be realized one of stable positions. Let us see the picture. It is the same that I said. So the picture. A is greater than B. A is greater than B. It means that they compete inside the population. What we see? We see that all our curves are going to the point P3. So the trajectories are like here. And P3 is a globally stable position here. And another picture. It is more interesting. If B is greater than A, B is greater than A, then we see the green line, this one. Green line that simply reflects this fact that what population is bigger at some point, this population will survive. So if we start at this point, then we see that the point P1 is stable. So it is our region of stability of the point P1. And it means that the first population N1 of 0 is greater than N2 of N2 of 0. And here N2 is greater than N1. And so far, the N2 population survives. So who is bigger wins. And the point P3 is a classical saddle. Classical saddle. So that's all about our competition. And what about symbiosis? Once more, there is another situation. If A is equal to B, it is another interesting moment because in this system, there is one unstable equilibrium P0 as usual, and an infinite set of stable but not asymptotically stable equilibriums on the line A N1 plus N2 quantity is C. And we can see that this line is in the first quarter of the coordinate plane. So all the red line is equilibriums, and our curves are close to simply the lines. Every one of these points, every of this point is stable, but not asymptotically stable. What does it mean? For sure, we'll never see it in the real biological models. There is a rule in the real biology. We never consider any equalities. In the real life, the coefficients can vary depending on some external factors. And so far, A and B are always changing with time, and we never consider any equalities. So this moment when A is equal to B, we can consider as the bifurcation point. We have seen that the picture when A is greater than B and when A is smaller than B are completely different. That's why we see this strange picture. One dynamic type becomes another dynamic type, and on the borderline there are there can exist something crazy. But in the real life, what can we see? If A become close to B, then at some moment our stable equilibriums will become unstable, and the point P3 will become stable. So we do not expect to see this picture. We'll see one or another. Next, a task for you. You can consider the general case when our C1, C2, A11, A22, and B are all different. And you'll see that these more complicated systems have absolutely the same dynamics. And the result is listed below. So zero solution is always unstable. And then P1 and P2 is a saddle or a stable node, and P3 is a stable node or a saddle. These need much more calculations, but the result is the same. That's why we consider two same populations. We can see that this inequality was our A greater than B. It is the same meaning. The same meaning. So next model is symbiosis model. Not that usual in the real life, but still sometimes it exists. So the sign of B is changed from negative to positive here. And the same analysis give us following result. We have 4 equilibrium points. We just can substitute in the previous model b by negative b, and we'll have the same. But what is the difference? First of all, if b is more or equal than a, there is no point P3. And moreover, you can prove that if B is greater than A, then for any positive initial data, both of the population are going to infinity. We understand that it is not a real situation. It reflects that fact that the interspecific interaction usually cannot be more strong than interspecific competition. So they cannot help each other with this strength. Usually it is not possible. So it's a not real situation. All our steady states are unstable, and their solutions are just going to infinity. And the second case is more real. When A is greater than B, then we see that all the fixed points are unstable, and the only one is stable. So in this system, the symbiosis guarantee us the coexistence of 2 populations. So it is the first situation, the symbiosis model. We see that the coordinates of our coexistence situations are bigger than the coordinates of a single population. That's quite natural. If they help each other, then when they coexist, both of populations will grow. And in the competition case, the coordinates of the point P3 always is smaller than the coordinates of our single population. And the last one, the situation when all the population are going to infinity. Another problems for you. Try to analyze these models and consider the equilibriums and give the conclusion of the results. So a predator pre-model with lower critical population of victims, in this case, lower critical population, and the second equation for pre, there is a multiplier p. It is less than 1. It means that not all the raised biomass is processing into predator biomass. When the wolf is eating the rabbit, he kills all the rabbit, but eat only some part of it. It means that it is not the same that the loss of the, here is the biomass loss for victims is B and 1 and 2, and the income of biomass is only P, B and 1 and 2. And in this model, we consider the situation when the predators do not compete. So far, consider this model and do the following. First of all, find the coefficient for the linear transformation of variables. Find the coefficients under which the initial system can be rewritten to this form. So there are only two constants here, L and A. Next, draw the integral curves describing the dynamics of the population density. First, in the absence of predator. The second, find the equilibrium positions and investigate their stability. And finally, draw phase portrait. So draw this one when here U and V, and draw the parametric portrait for L and A. What is a parametric portrait of our system? Let us come back, for example, to this model. The dynamic of the system depends on A minus B. So we have only one-dimensional picture. So at this model, A minus B, 0. This is the first region. The first region when A is greater than B. And this is another region when A is less than B. So the parametric plot is only one-dimensional, or in other words, we can draw A minus B. We can draw a picture. If A is less than B, then this picture, and if A minus B is positive, then the picture is like this. So it is the parametric plot of our system. When we consider Kolmogorov model, this is our parametric plot, and we can draw it on 2 dimensions. It is sigma, it is A minus B. So if A is less than B, then both of these quarters are this picture, and when A is greater than B, when sigma is negative, it is this picture. And this one is here. So we draw 4 plots. And this is our parametric plot for our equation. So this one and these two options. So finally, it is the task for you. Find the, I'm sorry, I missed M. So there is one more coefficient. There must be M. But I don't think the plot will become 3D. I think in this model, there must be some combination of these coefficients. Okay, another model with the same task. Let us see what's happening here. It is the model with shelters. The model with shelters. In the shelter, the population is protected. From the predators. So it is the population of victim in shelter. In the shelter. So the predators, there is no predators here. In the shelter, they are safe. So they just only limited by themselves. And the second, these are victims outside the shelter. Outside the shelter. The coefficient D N1 minus N2, it is the transition between the shelter and the outside. The transition between shelter and outside. And outside the shelter, there is the lower critical value. The equation with lower critical value. And the same, the transition of biomass. So our predators can hunt only outside the shelter. So it is the transition of biomass from our victims. So the dynamics will be like this. The victims replenish at the shelter, then they are going outside the shelter and they are hunted. If the population in the shelter becomes too big, then they are going outside. And it is okay for our predators. The problem is the same. Find the equilibrium positions and find out the nature of the stability. There is a lot of coefficients, so maybe you have to decrease the coefficients number first and then try to analyze it. It's not that complicated. You are just doing the same. So you are simplifying the model to decrease the coefficients number. Then you find the equilibriums. And finally, you investigate the stability. For example, well, we can see that the last equation. What are the what are our equilibrium positions? If negative C3 and 3 plus P, B, and 2 and 3 is 0, then N3 is 0. So it is the population without our predators. So it's just transition of victims inside and outside the shelter. And another one, if N3 is not 0, we can divide by N3. And N2 is C3 divided by PB. And then we can apply these N2 to the first and to the second equation. And finally, we'll get an equation for only one for N1. So it doesn't look too complicated. Well, the final part of our equations that are derived by ordinary differential equations, n-species model. The models becomes more and more complicated, but we'll just make a little touch of it. So we're gonna formulate some theorems. And we'll not try to go too deep inside. So when we have community of n biological species, the equation for them is the same Volterra equation. Ci is the rate of natural growth or mortality of ith species if there is no all other species. So the sign of Ci, if it is positive, it is our victims population, and if Ci is negative, then it is a predator population. And the matrix Aij reflects intraspecific and interspecific interaction. So far, the matrix A is called the community matrix. Or the matrix of pairwise interactions. First of all, let us assume that there is at least one of coefficient Ci is positive. Otherwise, all the species would be predators, and they should extinct because there is no external support of the biomass. All our predators will extinct. It's quite natural. Next, let us consider the simplest case, the predator pre-model with the complete transfer of the biomass from pre to predator. So we can see the situation when the matrix A is skew symmetric. So Aij is negative Aji. What does it mean? It means, for example, our classical Volterra predator pre-model. Next, since we are in the biological meaning, we can see that the set n plus So we consider only positive population densities, population numbers. And let us suppose that there is at least one equilibrium position in n plus. So first of all, if this equilibrium exists, it must satisfy the following equation. So the right-hand side of our differential equation must be equal to 0. We see that there is a trivial solution in our system. It always exists. And since among the numbers Ci there is at least one positive, then trivial equilibrium solution will be unstable. So the linear approximation matrix will have one positive eigenvalue. So from the equation 30, sum of ni will be equal to 0, and some of them will be positive. What does it mean that sum of the ni is equal to 0? It means that in the big community of n species, our steady state means that only k of them can coexist. So let the first k are positive and the last k plus 1, k plus 2, and so on, n, they extinct at our equilibrium. So we renumber the variables so that the first k are positive. K are positive. So we have still n equilibriums, but the first k are positive. Then we can consider our Lyapunov function the same as for Lotka-Volterra equation, the same one. For our first k equations in this form, and for last n minus k equations, simply ni. We can prove that the function is equal to 0 at the equilibrium, and it is always positive outside. One can check that the function v is the solution of the system if k is n and aii is 0. So if there is no interspecific interaction and if all the species survive, then the function v is the first integral. So it is the solution. Next, we can differentiate the function v with respect to the system 31. And then we take into account that matrix A is skew symmetric. Now becomes something complicated. So we calculate our differential with respect to the system. Then, we calculate dv, and then we substitute n dot with the right-hand side of our equations, and then we use that the matrix A is skew symmetric. So, for example, Aij, Ni, and j. If I and j from 1 to n, it is simply the sum of aii and I square. Because others are, they destroy each other. Aij is negative Aji. So finally, after some calculations, we get this result. Here, there is a negatively. So ni minus ni tilde square, it is always positive. Ni is always positive, not negative. Okay, not negative. And so this sum, the first sum, depend on the sign of aii, and the second sum depend on the quantity. So finally, we can formulate the theorem of stability. What do we need for stability? We need that aii will be non-positive, and the quantity will be not positive too. So finally, the theorem is valid if the species have the interspecific competition, and if these equations are valid, then the equilibrium state n tilde is stable. And if the inequalities here or here are strict, then the stability become asymptotic. And moreover, it becomes global asymptotic stability, so there is no more equilibriums, and all the solutions are going to the stable equilibrium state. An example of using this theorem, let us consider a three-species model, and let the first two species feed on the third. So one victim and two predators, predator 1 and predator 2. So there is our victim, and both of predators are fed by the third population. So what's going to happen? That's the question. Now the signs. C1 and C2 are negative since they are predators. A13 and A, this is negative. This is positive since N1 and 2 are predators. And the third is the victim. So it have opposite signs. Next. Let us introduce the notation. M is C1A23 minus C2A13. First, we consider the situation when M is not 0. Then, under this assumption, the system will have three equilibriums. So the trivial one and two non-trivial equilibriums. So in the first equilibrium, the first predator dies. In the second equilibrium, the second predator dies. We see that both of the equilibriums means extinction of one of predator populations. So when we apply the theorem for our points M1 and first of all, the point M0 is unstable as usual. And when we apply the theorem for points M1 and M2, the inequality for M1 have the following form. So we just use these. We rewrite the number of our populations so that the population with 0 coordinates is the last, and then we apply the theorem. So we apply this inequality. Now, for the point M1, the inequality 36 is M greater than 0. It is the same. It is the same. So far, the point M1 is stable for positive M. We do not consider M equals to 0. And one can prove that if M is less than 0, then M1 is unstable. Next, the inequality for the point M2 finally give us the opposite result. So M2 is stable for negative M, and M1 is stable for positive M. So far, we see that both of these inequalities are mutually exclusive. That means that only one of 2 points can be stable, M1 or M2. And finally, it means that one of our predators will extinct. There is a global principle that the number of predators cannot be odd. So it cannot be 2, 4, 6, and so on. There can exist 1 or 3 or 5. It is, well, we can't prove it, but it is the global principle. And in the real world, we do not see these situations that two predator species are fed only by one victim. They usually share a lot of victims, and so there is some specialization in the hunting and so on. For example, a wolf and the fox, they both can kill a hare or a rabbit, but wolf is better, for example, in going after the rabbit because, well, it is more durable and so on. And for example, the fox may be quicker, maybe the dexterity of the fox is higher, so the fox have some another positives comparing with the wolf population. Otherwise, they could not coexist. There is a more effective hunter who takes all the result, who can kill more than opponents. What is next? What is next? A bit more general case. A bit more general case. We considered only the situation when the matrix A was skew-symmetric. Now the general case. We can consider the value P equal to sum of some coefficients gamma I multiplied by Ni. So it is the total biomass of all our populations. And here gamma I reflect the different size of one species. So gamma will be higher for elephants and smaller for rabbits. And we can calculate P prime. So we can calculate the change of biomass. If we look at the right-hand side of our equation, we'll see that it equals to sum of the natural growth, the first sum, and another, it is the intraspecific and interspecific interaction. Let us denote the quadric form or quadruple form. No ideas what is the right pronunciation, quadric form or quadruple. Well, quad form. So it is the sum gamma I Aij and I and j. And according to Valterra, there are two large classes of such systems, conservative and dissipative. What do it mean? We know that the form can be positive or negative or neutral. So we have some conditions for example, negative that ensure that the form is negative. So far, we call a system conservative if there exists a set of positive numbers gamma such that the form becomes equal to 0. And if we can choose gamma 1, gamma n, so that the form become always negative and equals to 0 and at 0, then we call the matrix dissipative. Conservative for 0 and dissipative for negative form. First of all, one can prove that A is dissipative if and only if there exists the matrix, the diagonal matrix B, such that the matrix BA plus A transponent B is negative definite. It's not that complicated. We just rewrite what these metrics mean. And we see that it is just the same. And next, there will be some theorems on conservatism and dissipation, but I want to focus on them on our next lection on Saturday. So let's make a 15-minute break and turn to our presentation. Okay?
I'm sorry for interrupting, but I wanted to ask when it will be possible to present our reports.
So you can present it in 15 minutes.
Okay.
Mhm. I want to add that I'm gonna provide you with this presentation and with books needed. The first part, this part, there is a book in Russian very close to this, so you'll be able to prepare. And another part of our lections, there is a book in English, but I think it will be really useful in preparation when you will prepare for the exams. Okay, so that's all. And I'll be back in 15 minutes and we'll turn to presentations. Okay, if you are ready, we can continue.
Okay, and I'm just sharing my screen and should start.
Yeah.
Okay. So can you see my screen?
Yeah, it's okay.
Okay, so let's start. Today I'm going to talk about extreme ultraviolet lithography and what it is. It is an optical lithography technology using a range of extreme ultraviolet wavelengths. Just imagine a 40 kilowatt laser in a vacuum shoots a drop of 13 and turns it into plasma. So more about it. Um, photolithography is the most common method for fabricating integrated circuits, most known as electronic chips, such as solid-state memories or microprocessors. Um, about this optical lithography. It is a general term used for techniques that use light to produce minutely patterned thin films of suitable materials over substrate to protect selected areas of it during the subsequent etching, deposition, or implantation operations. I want to briefly talk about the creation of processors. So on the left picture is about the CPU derived from sand. Sand is made of 25% silicon, just behind oxygen, which is the second richest chemical element in the Earth's crust, and is a basic component for semiconductors for manufacturing industry. After purchasing coarses, sand, and silica separations, excess material will be processed and silicon refined in several steps to finally achieve the quality of semiconductor manufacturing, known as electronic silicon. After this process, there is performing silicon melting, and the result is a single crystal block, monocrystal. It's called an ingot. Single crystal blocks are produced from silicon at the electronic level. The block weighs about 100 kilograms and has a purity very close to 100%. Then the single crystal block will be cut thinly into semiconductor disks, or it's called wafer plates. After the cutting phase, these wafers will be polished until they have a smooth surface. Blue liquid, as shown below, is contrast material like the one used in film cameras. In this step, the wafers will be rotated so that the contrast material can be evenly covered, smooth, and thin on it. Next step is exposure with ultraviolet rays. This part will be revealed later, but I can say that at this stage the anti-reflective finish will be exposed with ultraviolet light. The chemical reaction activated by this light is similar to what happens to film material in our camera as soon as you press the shutter button. The areas of contrast material on the wafer that have been exposed to UV will become the soluble. There is used masks as templates, and with ultraviolet lights, it creates a different circuits pattern on the wafer. Creating of major CPU repeat this process continuously until multiple layers are stacked, and I talk about this later. Lens, middle part of the scheme, reduces the image of the mask to a small focus. The print results on the wafer is usually 4 times smaller than the pattern of the mask. The image below, middle, shows what transistors looks like when we viewed with the naked eye. Transistors are considered electronic switches controlling the current in computer chips. After exposure to ultraviolet rays, areas with exposed blue contrast material will be cleaned with a solvent. This will reveal the contrast pattern made by the mask. The reflective layer will protect the semiconductor material from being cleaned, and exposed areas will be etched with a chemical. After carving, contrast material will be removed, and you can see the desired shape. This is the step where no, sorry, second picture, where ionic particles are exposed to water, altering the chemical properties of silicon, so that CPU controls are current. Through a process called ion implantation, some form of doping process, the wafer exposures are etched with ions. The ions that are implanted in the wafer will change the way silicon in these areas the wafers are fed into copper sulfate. At this stage, copper ions are deposited into transistor through a process called electroplating. Copper ions travel from anode to the cathode. In the second picture, copper ions will be arranged into a thin layer on the wafer surface. And many metal layers are created to connect between different transistors. Although computer chips look extremely flat, they can hold up more than 20 layers to form complex circuits. If a room is large, you will see a complex network of wires and transistors that look like a multi-level highway system. And finally, a small part of the finished wafer will be put into the first functional test. During this phase, the test sample will be included to each single chip and monitored, comparing the response from each chips. After the test determines that the wafer has a good performance in processing devices, it will be cut into pieces called die. The dies that respond properly to the control patterns will be moved to the next step, packaging, and the bad dies will be removed. Of course, in addition to photolithography, other processes are involved in the production of processors, such as etching and deposition, and in fact, the combination of these processes together with the photolithography, transistors are, as it were, printed on a piece of silicon, layer by layer. But the technology is not new. Almost all processors since 1960 have been produced using photolithography. It was this technology that's opened a world of field effects transistors and the paths of all modern microelectronics. And the really big leap in this area occurred relatively recently, precisely with the advent of EUV, extreme ultraviolet lithography, and all because of wavelengths of 13.5 nanometers. The fact is that wavelengths with which our flashing shines is an incredibly important parameter. It is it that determines how small you can get the elements on the crystals. The periodic enhancement in the resolution achieved through photolithography has been a driving force behind Moore's law, if you know. Resolution improvements enable printing of smaller geometries on an integrated circuits, and the minimum feature size that the projection system typically used in the photolithography can print is given approximately by the next equation, where CD is critical dimension, lambda is wavelengths that we of light used, Na is some aperture of the lens on this stage, and K is a coefficient that's calculated for each process. So on the charts, you can see two red lines. The top line shows the development of DUV technology, deep ultraviolet lithography. It's placed there, and according to the formula, its limitation is 50 nanometers. And you may ask, but how then we hear about processors with 14, 10, or even 8 nanometers processor technology? But it's simple. There was a technology of multiple exposure using several different masks, and but the more such layers of masks, the higher the rejection due to the accumulation of error. On this slide, you can see difference between the work of a multiple exposure DUV and EUV lithography. The difference is obvious. The boundaries is much clearer. The geometry is better controlled, and the process itself is much faster. The percentage of defects is lower. That is, in the end, it's cheaper. EUV technology appeared a long time ago in the early 2000s. However, 20 years of development has made it possible to solve the following problems. The first, the problem with such short wavelengths is that they are absorbed by almost all materials. So the usual lens that used to be are no longer suitable. This requires ultra smooth lenses with a lens roughness error of less than 0.5 nanometers, which is already close to the size of an atom. Second is EUV dissipates even in the air. Therefore, it's necessary to do it all in a vacuum. The problem, the third problem, is that neither bulbs, nor lasers, nor any other normal light sources that emit such wavelengths simply do not exist in nature. Therefore, it is necessary to heat thin vapor to temperatures 1000 times greater than the surface temperature of the sun. In the installation for the production of processors by EUV lithography, which we will talk about separately, a special carbon dioxide laser with a power of 30 kilowatts is installed, which shoots two pulses at a frequency of 50 kilohertz. The laser hits thin drops. First shot actually flattens and turns the drop into pancake, and which becomes an easy target for the second volley, which sets it on fire, and it happens 50,000 times a second. And the resulting plasma emits light in the extreme UV spectrum. And of course, this is only the very basics, but I tried to paint you a picture of how it works. I think that's all. So.
Okay, thank you. Oof. Interesting. A bit complicated. Well, I have no ideas about this technology. So you said that all the problems were solved. And what about use of this technology nowadays?
It's because we faced a problem with nanometers, and DUV is cannot give us nanometers that we want, because it's it have some problems with it because of temperature and as I know information transitions, and for it no. As you see on the left picture, we face the problems to print these thin patterns with the DUV. So there invents the EUV to help make less nanometers tech process with less expenses.
Mm-hmm. Okay, so as far as I understand, we are really very, very close to atom radius. So yes, this picture. So 1 nanometer, it is 10 angstrom. So it is really close to atom size. So
Yeah.
will the progress?
And it has a problem that electrons just transit from one side of transistor to second, and this problem is not already closed or resolved.
So can you say that the progress in transistor producing is over? Is it the final technology? Or
No,
maybe...
it's not final, but I think we have computers that have not only two phases, 0 and 1, and maybe this will help us to reach new speeds of
so you think
microprocessors.
Quantum computers will be the new the new PC? But it seems that they will not replace our usual PC because they need too complicated environment. They need be
Yes,
freeze too much and so on.
but our computers before are too should be installed with very specific environments. But now it is very thin computers with 2 or 3 kilograms, or our phones with 100 grams. So I think in future we can apply quantum computer.
Right, but there are some problems with the technology itself. If we have to freeze something to negative 200
63, yes.
Celsius, so we need some external source of this code and so on. So it's really hard to make it smaller, just because of external facilities needed. And what about this technology? Can we decrease the length of our light more?
No, because of these problems. Because extreme ultraviolets already faced many problems, and I think in X-ray wavelengths it will be there is more some issues that we cannot resolve now.
But it is another way. So turning from visible light to ultraviolet and so to X-ray diapason, it will theoretically give us better result, right?
Theoretically, yes, but I don't know how to.
Well, we are just trying to imagine, so why not? Okay. Okay, thank you. Have you any questions?
I don't think so.
Well, so thank you. Who's next? How many presentations do you are ready for today?
Uh-oh.
No more?
I guess not. I won't probably be ready until like after next weekend, personally, sadly, because I'm gonna have to be going away for a bit. So.
Okay. So it's Monday. We have the same practice on Tuesday. What about Tuesday? Tomorrow? I have to check your list. Is there anyone in the list? Just a moment. I'm checking the Google document. It seems that only one tomorrow. Well, I think you have to hurry up because our lections and practices are very short. It is like 1 month. So if you will be not ready now, you have no time later.
Of course. I'll try my best, at least personally, but I think this goes for everyone else too.
Okay, so push everyone. Well, thank you. If that's all, yes, I see the only one presentation for today, really. Okay. Well, so see you tomorrow.
Can I ask a question?
Yeah, sure.
Maybe if there is only one presentation for tomorrow, I will present it on Saturday.
Well, let's do it tomorrow because I have no ideas how many of you will be ready for Saturday. So if you're ready, it's okay. Let's do it tomorrow.
Okay.
Mm-hmm. Yes, I want to sleep as you in 9 o'clock, but we have the timetable and we have to respect it still. Okay, so see you tomorrow. Goodbye.
Okay, goodbye.
Goodbye.
Bye.
Goodbye.
Goodbye.